kind of be like a review of transformations almost, because it's just doing more than one transformation at a time, but it'll kind of be like a natural review of rotations, reflections, stuff like that. Then Monday, I was talking to Ms. Lamb and my other co-teacher, and I think on Monday what I'll do is I'll give you guys an option. I'll have the lab card here on Monday, and if you want to work on Khan Academy, because you feel good about everything, or whatever, you just want to work on your assignment, because the next time is due Monday, I'll have that available for you, and one of us will go with those people. And then for everybody else, we'll do like a test review for Tuesday, and then you just pick which one you want to do. So symmetry, right? These are some key words to know. Throughout the lecture, we'll explain what they mean. Lines, symmetry, line of symmetry, and rotational symmetry. Think of line symmetry and line of symmetry, associate those with what you knew before. Can't wait to never use this thing again. As axis of reflection. Okay. And I mean, I guess it's in the word, but associate rotational symmetry with what we already know about rotations. Those are the two transformations that are involved in symmetry that you need to know about. So here, let's go slide by slide. I even have a neat little thing to use on the slides today. Just out of curiosity, does anybody already even actually have these in their notebook? Because they went online and kind of, these are all of you, if you are diligent and stuff and you're on top of things. All these notes are in the e-class ahead of time, so you can always write them in your notebook. I think for the next unit, one of the things I'm going to do just to also, again, limit excuses besides changing the homework is I'm probably going to start just printing out all the notes for you. Just because I just don't, you know, I want to limit let's not even use the ugly word excuses. I want to limit the reasons for us not understanding things. Try to be a better facilitator. So a figure has line symmetry or reflects. Look, they even use the word reflection. If it can be reflected across a line, remember axis of symmetry, or that the image coincides with a pre-image. The line of symmetry is also called the axis of symmetry and divides the figure into two congruent halves. So what does that look like on the right there? In black, what does it look like? It's a heart. That heart has line symmetry, but it has vertical line symmetry. The only way that you can like cut it in half, where each half is the same, is where each half is like a reflection of each other, is if you were to slice it down the middle vertically. If you were, you know, a heart does not have horizontal symmetry, because if you were to draw a horizontal line, the top half doesn't look the same as the bottom half. That one only has vertical symmetry, but there are some shapes that have, you know, horizontal, vertical, diagonal, that have multiple lines of symmetry. But this heart only has one. All right, cool. Now here starts the cool stuff. So tell whether this figure has line symmetry, and if so, copy the shape and draw all lines of symmetry. I know it might be hard to draw this, but see if you can draw that shape on your paper. So let's first answer the yes or no question. Does this figure have line symmetry? Is there any way to slice this where each side would look the same? Yeah, what are the obvious ones? Vertical, definitely, sure. If I draw a line straight down the middle, vertically, each side is going to look like a mirror image of each other. Any other ones? Yeah, this actually does also have horizontal. Any other ones? There's two diagonals. Yeah, so watch. Here's this is the one neat thing I found with the software, but it still was a pain in the butt to try to do. But woo! A little magnifying glass. So the first answer was yes. There are 8 possible lines of symmetry. Um, 1, 2, 3. I'm seeing 6. Where are they getting the other? Oh, because they're getting the other ones. Wow. Okay, so I guess I should maybe show you that drawing it. Okay, so the first ones that we said were obvious were vertical. Oh no, we have a line tool. We use the line tool. So the first one. There we go. So the first one is vertical, horizontal. Okay. Then we also noticed this diagonal and this diagonal where it goes right through like the I guess the inside of the star. But that's only 4 lines of symmetry. What they're claiming here also is that if you go through the like the corners, then it's also symmetrical. So if I were like to draw a line, like for instance from here, and I guess that's true. Can you see that? Mm-hmm. If I slice it that way, I each have 4 pieces. No, wait, 1, 2, 1, 2, yeah, four pieces of the star on each part of the blue line. They also sliced it through this corner. Right. 1, 2, 3, 4. 1, 2, 3, 4. Yep. Through this one and through this one. But those are a little bit harder to see. So. Yeah. One of the things you'll learn is that this figure actually also has what's called rotational symmetry, meaning I could also get the original figure rotated and get it to look the same each time I rotate it. Any questions there? Okay, so whether this figure has line symmetry. Jaden says no. Does anybody disagree with Jaden? Mm-hmm. Is there any line that could be possibly drawn to get this to look the same? Nah, it doesn't look that way. And let's reveal. Woo! Yeah, there's no line symmetry. Yeah. There's no line that could be possibly drawn. Like on your paper, if you were working on a quiz, you try to get your pencil, which conveniently has an eraser, and you would try to be like, well, how about maybe like this? Nah, that doesn't look the same. I definitely can't do anything like this. That's not gonna look the same. Like you basically try on the corners, try to come in on the corners, but there's no way to make them look the same. So this doesn't have any line symmetry. Or rotational symmetry for that matter. Okay? So whether this figure has line symmetry, and it show, copy the shape and draw all lines of symmetry. So is it a yes or a no? Yes. Yeah. What are the obvious ones? Horizontal. Yeah, this obviously has horizontal, vertical symmetry and horizontal. Those look the same. Do we have any more lines of symmetry? Yeah. Yeah, it looks like if we came in diagonally from the corners, that would also be a mirror image of each other. If we connected, that would look the same. That would look the same. I don't see any other ones. Let's see if maybe we're ignoring some of them. 4 lines of symmetry. So we got it right. Ooh. You guys confused. You're Joseph, and then he's what's your name? Did I get you guys confused? Ryan. It looks nice, but no. Any questions there? Okay, let's keep on going. Check it out. Tell whether your trigger has line symmetry, and if so, copy the shape and draw all lines of symmetry. So the same thing, but now with 3 of these. Let's just go one by one. How about A? Does A have any line symmetry?
Yes.
Yeah, definitely. I'd say yes. How many?
1, 2.
Yeah, I could see at least 2. If you come in diagonally, I don't know. I guess you'd have to. It gets be close. Let's see if they say diagonally 2. No, they're only saying 2 lines of symmetry. I guess it's because those diagonal lines are a little bit offset. I think that would have to be why. 2 lines of symmetry. All right, how about the B? How about the letter B?
Yes.
Yes and 1. Sure. What direction would that 1 be?
Horizontal.
Very good. Horizontal. Okay. How about that flag?
Yes.
Be careful. Well, yeah, it looks like it. Just be careful. Like, try to look at the stars. I know the shape of the flag itself looks like it has horizontal symmetry, but try to look at the stars and make sure you end up with the same amount of stars on each side. So, like, it looks like this star here is causing some issues. Maybe I might be wrong. Maybe I hate problems like this because, maybe that they meant one thing by it, but I'm interpreting it wrong. So I'm kind of curious myself. I don't remember what the answer was for that one. So the point I'm trying to make is, okay, it's obvious that the outside shape has symmetry that way, but if they're gonna color it in, it's supposed to be like everything's supposed to be symmetrical. This circle in the middle certainly is, but the stars look a little bit off. Here I have 1 star on each side. That's good, but then like this star over here,
It's the same as the one on top.
I don't see one in the same position up there. There should be. Oh, you're saying the same as this one up here? As that one?
No, it's kind of like.
It looks a little off to me.
We'll do the reveal then.
Let's see. Let's see the reveal. Let's see if she's right. Let's be right. Teacher be wrong. Yeah, look at that. They said yes. So. I was right today. The teacher was wrong. It still looks a little bit off to me.
Yeah, we counted.
Counting looks like the counting part looks like it would work because I see 6 above and 6 below. So the counting part isn't the issue. It's more the positioning of it. But okay, fine. Close enough. Okay, rotational symmetry. This one's a little bit harder maybe. Because they're going to ask you 2 things. Rotational symmetry, if it can be rotated about a point, blah, blah, blah. Okay, let's get to here. You're going to be asked for the angle. The angle of rotational symmetry, and the order. So the angle is how many degrees it would have to rotate before it starts looking the same. The order is how many times that could happen in 360 degrees. So like, if the angle of rotational symmetry is 90, the question is how many 90s fit into 360? 4, then that becomes the order. If I were to get, let's see if the wonders of technology would help me out here. Probably not, but let's see. Take out the fill. It'll look better without a fill. Let's do that. And of course it's still. if I were to get this and rotate it, how long before it starts to look the same? 90 degrees. Okay. How long before it starts to look the same? 90 degrees again. 90 degrees again for a quarter turn. Then the last part order says, well, how many of those, how many times will it coincide? Like how many times can it be rotated within a full circle? And in this case, there's 4. There's 4 different ways to make it look at the same in one circle. Let's do some examples. Okay. Tell whether these have rotational symmetry or not, and if so, give the angle and the order. So let's look at A. Is there a way that you can try to visually rotate this? Well, let's see. If we were to do, like, let's say a quarter turn, we would have 3 lines going towards the left. And no, that wouldn't work. If you did a 180, but then now you'd have 3 lines going down and only 1 line going up. So I would say A would be no, because it wouldn't look exactly the same. That's confusion. See, A doesn't have any rotational symmetry. There's no way to get it to look exactly the same by only rotating. Now we're not doing lines now, we're not doing an axis, we're doing rotation. Okay. How about B?
Yes, because the circles are just never change.
Well, okay. I wish I could manipulate the image here. But if I were to get this and turn it 90 degrees counterclockwise, would it look the same? No, because now the flag would be facing up. But if you look really closely, if I were to get it and rotate it half a turn, this little concavity would now come here, which is still concave. This convexity would come here, and it would still be convex, and these lines would still be the same. So if I rotate it, it looks like half a turn would work. So how many half turns are there in one full rotation? 2. So the 2 answers to this question would be, what's the angle of rotational symmetry? 180, because that's a half turn. And then what's the order? 2. Let's just confirm that. And we're correct. Yes, sir.
So is it always by 90?
What do you mean, is it always by 90?
Do you always rotate by 90?
No, technically no. No, but I mean, like, the thing is with this one here, it just, if I would have gone 30, it's a good question. That's actually good. And the answer to that is no. Like, there could be 30 degrees of angle of rotational symmetry. It could be 60. It could be 45. There's certain common ones that'll be, like, I doubt you're going to see a 52-degree angle of rotational symmetry. Typically, it would be numbers that are divisible by 360. You know, what are the common numbers that are divisible by 360? 10, 20. But I would say the most common ones, if you want to write it down, definitely the most common would be 90, 180, 270. And actually not even 270, because then that'd be too much. But 90, 180, 30, 45, and 60. I'd say those are probably going to be the most common ones that you might see.
So how do you know how much to rotate?
Well, it depends on each figure. So here, let's look at C, right? Pick any given point. Like let's pick a point to start off, maybe here. All right. If I start rotating, how much of a turn would I have to do in order to make it look the same? In order for the pre-image to look like the image? It looks like 90, a quarter turn. If I were to get this and turn it a quarter turn, now this line here would be where this line is. And if I continue to go 90, 90, 90 all the way around, eventually, every time it would match up, and eventually I'd make it to 360. So the angle of rotational symmetry here would be 90. And what's the order? The order is, okay, do you understand the angle part? Okay, so get 360 divided by the angle. What's 360 divided by 90? 4. The order is always going to be 360 divided by whatever you get for the angle, or whatever Jaden gets. Okay? Tell whether each figure has rotational symmetry, and if so, give the angle of rotational symmetry and the order. Stefan, the first one's going to answer your question for you, actually. Does A have rotational symmetry? Yeah. Like if you pick any corner here and start to rotate it, eventually it's going to look the same, right? But how many degrees would I have to turn before it starts looking the same again? Not 90, no.
180.
No, he's right. He's actually right. Because if you can't tell, I was like, oh, but I don't have a protractor. How can I tell the degrees? Well, can you at least tell the order? The order you can tell. Because how many times can I turn it before I get back to where I started? 3. So, and you'd actually go backwards. Do 360 divided by the order to get the degrees. What's 360 divided by 3? 120, yeah. 120. If you didn't understand that, let me know. I'll try to see if I can explain it a different way. But Kyla, how many degrees are there in a full circle? How many degrees are in a full circle? 360. So the thing is, how many times can I rotate it until I make my way back to where I started and make it look the same? Well, it would be 3. Once I could stop here and it would look the same, then I could stop here and it would look the same. And then finally I would get back to where I started from. So how many rotations was I able to do and match up?
Wait, so is you turn it to make it look the same, or you turn it to the way it was supposed to be?
Where you're turning it and it would still look the same as it was originally.
So, wait, okay, hold up. So let's say you got it like that, right?
Mm-hmm.
You turn it once, it ain't gonna be like that. But you turn it twice, it look just like how it did before, right?
If here, maybe I can do it with a shape here. Let's get a triangle shape. Is that okay? Like, is it okay if I don't use the yellow on the inside? Because it's all yellow. Okay. So, if I get this shape here, put your eye on one of the corners. Let's just pick the top corner, right? You following it? Turn, 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 turn. Have I made a full turn yet?
No.
Does that look the same as when it started?
Yeah.
Yes. Okay. Keep on going, keep on going, keep on going, keep on going, keep on going. Have I made a full turn yet?
No.
No. Does it look the same as when it started?
Yeah.
Yes. So that's 2. Finally, have I made a full turn yet?
Yeah.
Now I have, and now it looks the same as when it started. So how many times, I just finished making a full circle, how many times within that circle did it look the same? 3.
So what you're saying is you're just trying to make it go to see how many times it is for a full circle.
Correct. In order to have rotational symmetry, you have to be able to turn it some amount, and after turning, and you let it go, it looks the same as when it started. So if that's possible, then the second question is, well, how many times can you do that in one circle and still have it match up? This can do it 3 times. So if it can do it 3 times, that means that each turn was 120 degrees because it's 360 divided by 3. How about the next one? That's actually known as a parallelogram. Remember that we're not doing this Jesus, actually, yeah, I want to say it also has a linear symmetry, and it would be, see what it be? Because if you flip it, yeah, I want to say it would be vertical. we're not being asked about linear, but just if we were to flip it that way, um, they have um, they have linear symmetry. If you were to flip it, it should be this way. No, maybe not. Maybe not that way. I don't know if that would work, but it should work this way too. And this way, like there's a few lines of linear symmetry, but here we're being asked for rotational. So is there a way I could rotate that parallelogram and have it look the same? How? Only half a turn. Yeah, because if I only turn it a quarter turn, it's gonna be tall and skinny instead of laying flat. But if I do a full 180, yes. And then Zyra, if my angle of symmetry is 180, how many 180s are there in 360? You don't know how many times? You don't know what 360 divided by 180 is? How many half turns are there in a full turn?
2.
2. How about the last one, which is actually a repeat of one that we had earlier? Oh, well, actually, I'll take it back, because earlier it was line symmetry. This is rotational. Is there a way to rotate that and make it look the same?
No.
It doesn't appear, no. It doesn't appear. You have to go full 360. Yeah, there's no rotational symmetry. Any questions there? Yes.
So if you have to do a full 360, then it's not.
Yeah, you have to go full 360 then. Every single shape, if you went a full 360, and it would end up looking the same. So that would kind of make it pointless. Ooh. This one here I kind of disagree with, but I remember going over this before. But let's see. Describe the symmetry, copy each shape, and draw any. Oh, so this they want lines and rotational. So does this appear to have line symmetry? Yeah. See, I agree with you. Like I don't think it has let's see, line. Because if you go to the top. Horizontal, like, yeah, yeah. This one shouldn't have line. I think it was the rotational one that I disagree with. Let's see. Yeah. See, there's no line symmetry there. So there we're in agreement. But does it have rotational symmetry? I see, but I would say no to that too because of the colors. See, because like if it's gonna have rotational symmetry, the most you could do is go half a turn, and then this part that's black background with a white dot would be down here, but the colors would be off. If they wouldn't have colored it in, and like both halves would have looked the same, then I would say yes. But like, I would say do the colors. No, kind of remember the flag. Remember how we were looking at the flag?
Well, it matters.
I would say it would. If we're talking about an image looking like a pre-image and the colors are different, I would say it is, but they disagree with me. So you're not gonna have any like on the test where like the color is gonna be an issue. I guess this is more. I mean, Miss Lamb, you can chime in if you want, but they say it does, that it has rotational symmetry. Like to me, this part here. Oh, I hate this thing. This part here doesn't look exactly the same as that part there because the colors are inverted. But I guess whoever wrote this problem would disagree with that.
So they're just basing it on the circle then?
Yeah, see, like I would have liked this problem better if they would have just done something like this, where here's your circle, then where now each part looks. I mean, I just hand drawn so far. pardon the crudity of the drawing, but something like that, yeah, I would say it has rotational symmetry. Because if I get this and rotate it half of a turn, then they would look identical. But in this case, the colors are inverted, so.
So you're just not looking at the colors.
Yeah, I mean, I would argue not. I would argue that there isn't rotational symmetry, but I guess they want you to ignore the colors here.
You'll see that though, if you ignore the colors, then it would have.
Okay, how about here? Describe the symmetry. So try to draw this on your own paper. And we want to know, is there line symmetry? So this is both. Is there line symmetry and is there rotational symmetry? Well, definitely there's going to be line. Let's start off with that one. So that's definitely going to be a yes. How many lines of, how many axes of symmetry does it appear that we would have?
4, 2.
Let's see. It's definitely horizontal. I think it's going to be more than 4. Oh yeah, no, it might just be 4. Yeah, you're right. You're right. Cause this is just 2. So horizontal, vertical. Then we got diagonal, where it would look the same. And yeah, that's it. There's no. Let's confirm. I can't wait to never use this thing again. Line of symmetry. Okay. That's the same thing we drew. So yeah, there are 4 of them. That's the same thing we drew. So that's the line symmetry part. How about rotational symmetry?
Yeah.
Let's just pick any point on here. Let's just say maybe right around here on the right side. And if I started to rotate that point around, when would it start to look the same? How many degrees would I have to travel? 90, yeah, like a quarter turn. Which means, what would the order then be? What would be the order of rotational symmetry? If every 90 is going to look the same again, what would the order be? Okay. Describe the symmetry of each figure, draw any lines of symmetry, and then give the angle and the order. So this is the same thing, do both line symmetry and rotational. The first one, okay, we definitely have line symmetry. That is both horizontal and vertical. Do we have any diagonal too? Yeah. Right down the corners. It looks if we flip that, that would be the same. And there. So how many lines do we got?
4.
Yeah, we got 4. How about rotational? Yeah. How many degrees?
90.
90. Let's see the grand reveal. Yeah, line symmetry and it has both. 90 degrees. The order is 4.
So when we write in this, we have to put 90 and 4.
Yeah, on the test on Tuesday for these, there's not a lot of them, but on the ones you do have, they're gonna ask you if they're asking you about rotational, they're gonna ask you for the angle of rotation and the order. Ooh, that's an ugly one there. That second one. Does it look like we have line symmetry?
No.
It doesn't look like it. And rotational?
No.
Doesn't look like it either. And there's no symmetry there at all. Does that make you go to the bathroom a lot? Yeah, I can imagine. Okay, so we're finished a little early. So tomorrow I have an activity planned for compositions, but I haven't I was never able to give you the notes on that, even though they're not that long. But let me just start those notes now, so that tomorrow we can spend more time on the activity. Remember, these are all online if it's too much for you to write. Just to be fair, and like since I'm the one grading it, I would let this slide if you were to write either one. But when you see this this word here, I don't even know if I'm pronouncing it correctly. But isometries, we call those rigid motions. It's the same thing. What I would like for you to tell me, since we knew them as rigid motions, what did all the rigid motions have in common? This will be on the quiz. So I don't care which one you call it isometries, call them rigid motions. I don't really care. But you need to know what they do versus the non-rigid motions. Can you at least tell me what the isometries are, what the rigid motions are? There's 4 transformations, 3 of them were isometries.
For the names of the things, the ones we've done.
Say it again. Translation is one of those, yep. Rotation, yes. And reflection. Those are the 3 that are rigid. Then the non-rigid one is dilation. How are they different?
It gets smaller. It gets smaller. Reflection goes
How many athletes do I have in here? And how many of you guys work out? Athletes. You consider yourself to be an athlete, and you work out. So we know a little bit about exercise.
Yeah.
Okay. When you are performing an isometric exercise, have you heard about different types of exercises? But there's ballistic exercises, isometric. No. Metric means measure. ISO means like static, like it doesn't change. So like when you're performing an isometric exercises, what's not changing in length? The muscle. The muscle's not moving. If you've ever benched, have you ever tried to, you pick up the bar and you go about half, you don't lock out, you go about halfway and try to hold it as long as you can? See how long you can hold it there? That's an isometric exercise. Because your muscle fibers are flaring, they're having to maintain the weight in a position, but at the same time, the muscle's not changing in length. Isometric, not changing in length. Well, an isometry, a rigid motion, it preserves size and shape. There's only one transformation that does not preserve size and shape. That one is the dilation, yeah, because that's what stretches and compresses. So all this lesson is just getting some of the transformations and just putting them together, doing more than one transformation at a time. So here, KLM has vertices. They named it for you. They want us to rotate it 180 degrees. And I'm scared to write on this thing because it's gonna let's see. So rotate 180 and reflect across the y-axis. Let's do both. The good thing, Ryan Ames, I know you're a little worried about this, is that we're rotating across the origin. Even if they did not give me an image, or in this case a pre-image, like if they didn't show it to me, I'd still be able to do this because I know the rules. So let's see who memorized the rules. Let's do K prime. K starts off at 4, -1. First, let's rotate 180 around the origin. Who remembers the rule for 180 around the origin?
negative y, negative x.
Negative x, negative y. Keep the x and y where they're at. Change both signs. So where are we going to be at first? We're going to be at -4, +1.
And you also have your half sheet. You also have that little sheet we gave you.
So -4 and positive 1. Okay? Then the last one, now that we left off at negative 4, positive 1, what happens when you reflect across the y-axis, which is the vertical one?
It'll be 4 and 1.
The x changes sign. Very good. So 4, 1. So this is going to be my final image there. K is going to be at 4, 1.
So see, all he did was rotate that point and now reflected that point over the y-axis.
Okay, so now let's do L prime. Same transformations. So let's go 180 around the origin. So it would be negative 5 and then positive 2. And then the last one would tell me across the y-axis?
5 and 2.
5, 2, fantastic. Now, one of the benefits of having a picture of the graph is that when you're graphing it, if the shape looks all distorted, well, you did something wrong because you understand that both rotations and reflections are isometries. They're rigid motions. It's not supposed to change. Whatever I end up with better end up looking the same. Okay, finally the last one. Just do this one in purple. M prime. First, let's do the rotation. Negative 1, 4. And then
1, 4.
And then 1, 4. So 1, 4 is here. That ends up being M prime. So when I connect the dots, that's what I end up with. Tomorrow we'll finish this. We'll do a few more of these, but I want to get through it quick because then do you remember the last activity that we did where we had the big grid and we filled it all in? Well, we have just one huge, massive composition of a transformation. We're gonna do a bunch of transformations all in one.